Thank you, Antoine, and thank you everyone for being here. Thanks as well the organizers, Raphael and Abhishek, for the invitation. It's a pleasure to be here. It's my second time at ICTS. It's a place that I truly love. One of my favorite institutes of theoretical physics. And yeah, today I'm going to talk about the effect of noise and monitoring in symmetry breaking and chaos. So essentially that divides the talk in two parts. But I want to start thanking my collaborators and my group in Luxembourg. I actually just noticed I miss a new PhD student, but essentially we have 3 postdocs, 3 PhD students, and here are some of the former group members, in particular Mitun, who's now in Bengaluru, just moved from Manipal to Bengaluru, and the group of Aurelia Chenou that Saclay talked yesterday, and you may already have heard about. Good. Since I'm in India, why not? I thought I would also take the chance of thanking many of the local collaborators. Over the years, I have had the pleasure to work with many Indian scientists, and this, apart from some fun in research, also came with lots of friendships. You may recognize Sabal Saxena, Krishnendu Sengupta, Prasanna Venkatesh, who was here, I think left yesterday, Rebati, Victor Mukherjee, Madhivakaran, Aritra, who is also a participant, Mitun, and Budaditya, who's in the audience, and Preeti, whose research was also presented in the talk by Manas, many others. Yes. Right, so I want to start with super basics. So, if we go to just the standard setting of the coherence, we find that if we prepare, so we typically have a density matrix that we get from some tensor product, assuming uncorrelated system. At time equals 0, we evolve it unitarily with rays, and we find a Lindblad form, which takes this form. So that's the very basics. Now, the phenomenology that this kind of equation can capture is maybe summarized in this example of the quantum Brownian motion, even if this is not strictly Lindblad, so it's only if you kill this term, it's Lindblad. There's the famous work back to Wojciech that saw that if you put a coherent superposition in the coordinate space, in the coordinate representation, this superposition dies away as a function of time as a result of the phasing in the position. And by looking explicitly at the off-diagonal elements of the density matrix, at short times, he figured out this approximation, and from there he read off essentially the time scale in which this superposition dies, and that's given by this estimate of the coherence time, which is just essentially telling you that you can look at the size of your superposition in units of the Broglie wavelength, and the inverse of the square of that gives you the coherence time. So that was, of course, a cute and early seminar result, but I wanted to systematize this in a way which is model independent. I don't need to read in a given basis the behavior of the density matrix. So what we did is something very simple. We look at the purity as a function of time. So this is constant if the dynamics is unitary, and it only changes as a result of the effect of the dissipator. So then we assume we have a Markovian dynamics, and then just Taylor expand the purity at short times in such a way that we can read off this leading the coherence rate, the inverse of which is just the coherence time. Now, it turns out that this allows you to come out with this cute, simple expression for the coherence time, which tells you that this is just the inverse of the sum of the covariance of the Lindblad operators evaluated in the initial state. So this is a generalization of the result by Wojciech to any other Markovian dynamics. I guess you can carry on with this kind of approximation to other evolutions as well, not necessarily Markovian. Right, and of course, within at order T2, this is consistent with an exponential decay, which is essentially the same level of approximation as Wojciech used in his work. So now that we have this estimate of the coherence time, I want to come back to the effect of noise. This is going to overlap a bit with the presentation of Aurelia yesterday. So I'm going to assume I have a time-dependent, in principle, deterministic Hamiltonian. Plus, I add noise to some other operator. So I have an operator B, whose coupling constant is going to fluctuate, or at least is going to have a noisy component governed by a white noise. And therefore, I can always formally solve the time-dependent Schrödinger equation. This is extensive literature in this. At least I know works by Gerard Milburn, Moya Thesa, Boudini has beautiful works on on this, and this is a paper we wrote with Aurelia Senou, Mathieu Bo, and Jan Schutzau at MIT. What you can do is to compute as we have seen in other talks, you average over different realizations of the noise, you add up all the state vectors you have solved from the stochastic Schrodinger equation, and in that way you get an average density matrix, the noise average dynamics. With no assumptions on the noise, you can solve that the equation of motion that this average density matrix obeys, it's a bit complicated, a bit nasty, because actually it depends explicitly on the stochastic realizations. I mean, obviously it's non-Markovian. There you see the correlator of the noise, that's very nice. But actually it depends on the stochastic realizations explicitly. So this is not very useful at this level. You can do two things. One is to do perturbation theory in the strength of the noise. That will hold even for color noise. Or you can just assume that the noise is white, and therefore you get a delta function, and you can collapse this into the dephasing in the eigenbasis of the fluctuating operator, which is on which I'm going to focus. So this is what comes next is this idea that we can we can use this to simulate complex open quantum dynamics. In particular, if we have a quantum simulator that allows us to realize something like an Ising model, we can either add noise in the magnetic field, and that will give rise to a dissipator, which is just the double commutator of the magnetization. And you can characterize the decoherence rate, or the coherence time in this case, and so that it decays polynomially with the number of particles. This is again under the assumption that the noise is global, but you can carry on the computation as well for local noise and get a similar estimate. So, you know, if I add noise to a one-body operator, then I have the coherence time as 1 over n squared. You could also add noise to the ferromagnetic or anti-ferromagnetic spin interactions, and then you get a kind of dissipator, which looks like a bit like a four-body dissipator in the sense that it couples four spins at different sites. And there you see that the coherence time using this formula with the covariance of the Lindblad operators, you can formally, I mean, compute everything, but you know, the scaling is with 1 over n to the 4th power, where n is the system size. You pick, this is actually what Aurelia mentioned yesterday, you make a fluctuating operator which is k-body, then you will find a dissipator which is 2k body, or at least couples 2k particles, or 2k spins. And if you estimate the coherence time, it goes as 1 over n to the 2k. So it looks like it's always polynomial scaling. And you may wonder, is always the coherence time decaying as a polynomial of the system size? Is there anything else? So this is the question we ask, whether there's something else beyond this decoherence, polynomial scaling of the decoherence rate or polynomial decay of the decoherence time. So one thing we did is to consider that the Lindblad operators is actually a random matrix operator. This arises in several contexts in quantum information theory and also in black hole physics. You can justify it in different ways, but in this case, we again use our formula for the decoherence time. In this case, it's just the sum of the coupling constants entering in the dephasing operator times the variance of the Lindblad operators. But now the game we play is that these Lindblad operators are sampled from a random matrix ensemble, say the Gaussian unitary ensemble of dimension d. And in this case, you can show that the coherence time scales as an exponential of the system size. It's no longer a polynomial, it's an exponential. So this we call extreme decoherence, and we claim that there cannot be a higher scaling of the coherence rate. Okay, so this is a first result, which is what happens to many-body Hamiltonians with stochastic fluctuations in their coupling constants. Now I want to move, this so far was essentially for undriven systems, so I want to see what's the role of classical noise when I drive a system. So what I'm going to consider is the crossing of a quantum phase transition by driving a parameter as a function of time in some time scale tau. I will tell you what's the Kibble-Suek scaling and then what is the anti-Kibble-Suek scaling. But it's going to arise as a result of noise. So let's look at an example and consider the paradigmatic transverse field Ising model in one dimension, which was the model which was used to establish the validity of the Kibble-Suek mechanism in the quantum domain. So the Kibble-Surek mechanism tells you that if you cross a phase transition in finite time tau, you produce excitations, typically topological effects in the classical case, or just excitations in the quantum case, that are going to scale with the time scale in which you have driven the process, with this time scale tau, as a universal power law. So in the absence of noise, you just say, vary the magnetic field. This is essentially telling you that you go from a large magnetic field when the spins are all polarized in a given direction to a case where the ferromagnetic interactions dominate, and then you will have either spins up or spins down. So the prediction of the Kibble-Surek mechanism always takes this kind of form. So it tells you that the density of excitations decays with the running time, with the driving time, as a power law, which has an exponent, which includes the dimensionality of the system, D, as well as the equilibrium critical exponents, nu and Z. So it's a cute result. It's very simple, very hand-waving, but it tells you how you approach adiabatic dynamics, so suppression of excitations, as you increase the running time across a critical point. So this is the prediction in the quantum case was established in this series of works by Polkovnikov, Tamsky, Yarmaga, Surek, Dorner, and Scholler in 4 independent papers. And here you have 2 experiments where it has been tested. One is in a one-dimensional Ising chain, and the other more recent in a 3-dimensional condensed matter system that behaves really like a 3-dimensional Ising model. So this is broadly applicable, and the Kibble-Surek mechanism has been studied for around 40 years, and it works. Yes. Now let us see what happens when you put noise. So typically many devices control parameter you cannot tune it as a beautiful linear ramp, but it has in addition a stochastic component. And I want to, in this case, just our modeling is just assume you have the linear ramp plus some noise on top of it, and the noise is going to be white again. So you can do what we have discussed already. You can solve the stochastic Schrodinger dynamics, so you can look at the noise average dynamics, and it will be a master equation in the white noise case with the phasing in the fluctuating operators to which the magnetic field couples. In this case, it couples to both the magnetization and the ferromagnetic interactions. So this is what you see. So in the absence of noise, so here I'm counting the density of excitations or the excess energy, so the mean energy above the ground state, and the density of excitations is just a kind of the average number of kinks. With any of the observables, the behavior is very similar. In the absence of noise, for W equal to 0, you have the beautiful Kibble-Surek power laws. This is a double logarithmic plot, and the power law of Kibble-Surek just becomes a straight line. But you see that as you increase the strength of the noise, then there starts to be the fact that as you go more and more slowly, the density of excitations starts to increase. So that tells you that noise is preventing the naive use of adiabatic strategies of just slowing more and more the dynamics to approach the adiabaticity is not a good idea in the absence of noise, because you have this growth of the density of excitations. This is what is called the anti-Kibble-Surek scaling. This is Kibble-Surek, this is anti-Kibble-Surek. And so it tells you that in the presence of noise, you cannot blindly rely on adiabatic protocols, and that the best you can do is, depending on the strength of the noise, there is a stopping point where you will reach the minimum density of excitations. So it's going this way. Yeah. So you can actually characterize this optimal stopping time, where the density of excitations, or the density, the minimum of the energy, or the minimum of the density of excitations occurs as a function of the strength of the noise. And you can see that actually fits a beautiful power law. You can very simply understand this power law by assuming that the density of excitations have 2 additive contributions, one coming from the Kibble-Surek scaling, the other one coming from noise-induced heating which occurs at a well-defined rate, is linear in time. That allows you to determine that the optimal stopping time scales with the strength of the noise in a universal way. And okay, so this is the prediction we have already almost 10 years ago. So sorry for presenting this old result, but I thought it was relevant to this audience. Now, more recently, there have been experiments verifying these predictions. So the first one is a quantum simulation experiment of is precisely the same model we discussed. And you see that they plot the density of excitations. Now this is experimental data, even if it looks very, very clean, but you see the error bars are very small. And they plot the density of excitations as a function of the running time, tau. And you see that in the absence of noise, you have this Kibble-Surek power law, but then there is this heating and this anti-Kibble-Surek scaling. They also characterize our prediction on the optimal stopping time as a function of the strength of the noise, and you see that there is good agreement with the universal power laws. So this was a quantum simulation experiment with an ion. So in some sense, it was slightly tautological, but you have to realize that the same physics is being reported in different kind of simulators. So this is a beautiful experiment using D-Wave devices where they embedded the two-dimensional easy model. And again, they studied linear ramps and reported as a function of the rate what was the excess energy and the excess magnetization. Here, this is a rate. So this is slow. This is fast. So when you go a bit fast, the Kibble-Surek scaling holds, and you have these power laws. Now, as you go slower and slower, you see that there's again this minimum, and then this start to grow the density of excitations. So this is, this was not. They were not trying to test our theory. They just find that in devices, you have sources of noise very much like the ones we consider that give rise to this anti-Kibble-Surek scaling. That was in kind of analog quantum simulation. If you consider a D-Wave device as a programmable many-body quantum spin model. The same physics is being observed as well in digital quantum simulations, where you trotterize the dynamics, and now errors in the trotterization also give rise essentially to this anti-Kibble-Surek scaling. So this is has reported very recently using IBM. They again embedded the I think an easy model. They drove it by increasing the annealing time, and you see a regime which is consistent with Kibble-Surek, but again you have this heating induced here. Not so much, it's just as a result of the gate errors and the trotterization. The dynamics is not continuous, it's discretized, and this induced to this heating. So this noise-induced anti-Kibble-Surek scaling is becoming increasingly relevant in the current quantum computers or quantum simulators that we have today, both in the analog case and in the digital case. All right, so this was the second part of the talk. So I keep moving. So now I'm going to leave classical noise, and I want to move to continuous quantum measurements and report, again, this is a bit of an old result 5 years ago, 6 years ago, on how monitoring a phase transition changes the way in which symmetry breaking occurs. So the scheme for quantum continuous measurements that I'm going to use has been already presented. I'm going to assume that I monitor some observables A alpha, and at the level of the average dynamics, if I throw away any measurement record, I will just induce dephasing in the eigenbasis of the operators I choose to monitor. And if I keep a single trajectory, so I do have a stochastic unraveling with a linear process, and this is what also sometimes is called the innovation term, which essentially makes sure that the trajectory is following the expectation value and purifies the dynamics. Right, so we stuck with our favorite model, the one-dimensional transverse Felicity model that we understand very well. And we want to put in this model the effect of the continuous measurements. We could do a ramp or we could do a sudden quench. It doesn't matter in this case how we are going to vary the parameters of the model. What is important is that I want to start in the paramagnet and I want to go to the ferromagnetic phase when the spin-spin interactions dominate the dynamics. So I'm going to choose a state which is the ideal, as an initial state, I choose the ideal paramagnet in which all spins are aligned in the same direction. And I do this in such a way to make sure that the magnetization along the z-axis, here sub-index is missing, I choose the z-axis, the magnetization is strictly zero. In the initial state is obvious, yes? This is aligned along the x-axis, so magnetization along the z-axis is zero. Now, if I drive the system either by a linear ramp or by a sudden quench, what I find is this remains the case at the level of the average over many realizations. So different trajectories, on average, preserve the magnetization. However, at the level of individual trajectories, I can see that so in this case, in the absence, if I average, there's no symmetry breaking, I have zero magnetization, I keep zero magnetization. It looks like I'm not learning anything. But now, when I choose to monitor, for instance, individual spins in this ising chain, what I find is that the measurement feedback associated with the linear process precisely give rise to a change of the local spin alignment, and this is going to give rise, this is what seeds symmetry breaking. Yeah? So you can see explicit computation shows that this is controlled by the strength of the noise. So the larger the strength of the noise, the fastest should be this breaking of symmetry at the level of individual realizations. So here you have it in pictures. So this is a plot of a spin chain. So this is the spin site, and this is time. So we start at the bottom, and we are moving forward. And this is for a weak measurement, a bit of a stronger measurement, and a much stronger measurement. Again, at the level of average, you will see just zero everywhere. The magnetization will remain zero. But here you see how, thanks to the measurement feedback resulting from the monitoring, you have a bit of symmetry breaking. You strengthen it, as you increase the strength of the measurement, then what you see is that now you start to have classical-like configurations where the local magnetization takes actually definite values, either positive or negative. So these are spin up, spin down beamform. And if you increase the measurement, this is already very much like a completely classical state. I have spin up, spin down, spin up, spin down. Good. So this is what happens when you choose to monitor a single spin, and this is a case where symmetry breaking occurs only at the level of individual trajectories as a result of quantum monitoring. It doesn't occur in the ensemble average. But why choosing to monitor spins individually? You could as well decide to look at the local magnetization over, say, k clusters of, clusters of spin of k spins, or you could decide to monitor the whole, choose an observable which is global and over the whole chain. Yes. So we are going to compare the dynamics between local, coarse-grained, and global. In this case, monitoring of the magnetization. I could choose another observable, but we choose the magnetization because it's related to symmetry breaking. And this is what you see. So this is essentially what I have already shown you. If you make a strong, yes, either you wait a long time and you make a strong, you increase the strength of the continuous measurements of the local spins, you see classical-like domains. But I find much more interesting what happens here. So if I choose to monitor, say, k spins, what you see is that you split the chain into subunits where no symmetry breaking can occur, so where no defects can occur. So all these k spins choose to go to say a negative spin configuration. It's a bit like if we were renormalizing the chain by clusters of spins. So you no longer can have these sudden jumps between neighboring spins. At most, there's a minimal length of units set by the monitoring agent. And what is also interesting here, this is where spin 1/2, then the magnetization could be only 1/2 plus or 1/2 minus. But here now we are having we allow for new values of the magnetization. We have, say, k spins, and it can take 2k plus 1 values of the local magnetization. As a result, the interface between adjacent domains is of a very different nature from the one we have in the case of single spin monitoring, because there we can only have one kind of defect, spin up, spin down. But now we can have local magnetization which take any of these 2k plus 1 values, and the neighboring spin can take, the neighboring cluster can take any of these values. So we are changing the pattern of symmetry breaking. What we have here is no longer what is called set2 kinks, where it's just spin up, spin down. We here can have different kind of kinks, yes, which again is completely governed by the monitoring agent. And if the observable that is monitored is global, then actually you can have no defects at all. But what can happen is that the magnetization now, the symmetry breaking, but only at the level of the global chain. So the chain remains uniform, no defects can be formed. There's a single domain, but this domain can correspond to different values of the magnetization. So if there's a theory of to classify topological defects and symmetry breaking in isolated systems, which are not monitored, and that goes back to the works of Tom Keeble and Mermin in the 70s. And typically what one does is to look at the symmetries of the vacuum manifold. You have a symmetry G which is broken, there's a subgroup which is left, and you look at homotopy groups to classify the topology of this vacuum manifold, and this allows you to predict what kind of defects you are going to have. Whether there are kinks, vortices, domain walls, spin textures, or like some skirmions, or something more esoteric. What we have seen in this numerical example is that by monitoring different clusters of spins, we go from a case where we have a vacuum manifold which allows only for discrete parity symmetry breaking to a different vacuum manifold where now I can have other orderings of the spins. So we have changed the topology of the vacuum manifold and the kind of defects we can have. And I guess I here pose what, for me at least, is an open problem. We had yesterday a nice talk at the end of the afternoon using symmetry classifications of Lindbladians, but I do not know how to generalize this very well-established theory to predict what kind of textures can I expect when I choose to monitor a given observable in a quantum system. So, what's the classification of topological defects of monitor quantum systems? A beautiful problem. As far as I know, there's no solution to this. So, if anyone in the audience or anyone around is happy to look into this. I have some thoughts, but I don't have the answer yet. Okay, so this brings me to the second part of the talk. So I'm now going to move from, I leave phase transitions and symmetry breaking, and I move to chaos. You may wonder why I chose this picture. I took it at, well, someone took it at Los Alamos. Los Alamos is full of mesas. This is New Mexico, so you have mesas, you have valleys, and you have more mesas, and you will see that this is going to be the basic phenomenology of quantum chaos in quantum systems. So quantum chaos has a huge history. I cannot possibly revise it here. There are similar results on how classical chaos can emerge from quantum chaos, and there are, there's a broad literature. There's several references you can focus. I'm going to choose to characterize quantum chaos by a quantity which is known as the spectral form factor. So the spectral form factor was introduced, I think, in the 90s, yes, 80s. Leviender, by Brummer in Toronto, Raphael Levin, and others. And they say, well, when I have a spectrum which is very complex, there are many eigenvalues, it's a mess to look at the real spectrum. So let me just take the Fourier transform and see what I get. It's a very nice thing. Turns out that the Fourier transform of the spectrum is just essentially the survival probability. You can just show it. So this has been used broadly. This is a picture of the, I think, first paper, one of the first papers. And more recently, in the community of high energy physics, emphasis has been shifted a bit to the analytic continuation of the partition functions to complex inverse temperature. But you can realize that this is just a subcase or an instance of the early result when you choose the initial state of a given form, a coherent Gibbs state. But anyhow, these two quantities essentially are going to be related to the spectral form factor. And you can show, that the overlap just has some local density of states defined this way. And when you take the absolute square value, so that's the fidelity, or that's the quantities that were introduced here, and you average over an ensemble, say an ensemble of Hamiltonians, of different Hamiltonians, that's a typical thing you do in quantum chaos, then you can rewrite the exact expression using three different contributions. One is a constant. You will see that it governs the long-time dynamics. One is going to depend on the eigenvalue correlations. So this is what is going to tell us about chaos explicitly. And the first one is just depending on the average local density of states, is going to govern the short-time dynamics, but knows nothing about chaos. Okay, so when you plot the fidelity as a function of time in a chaotic system, here I take the SYK model for the experts. It's just a canonical example of a system which exhibits chaos, maximal chaos. So this is what you see. The fidelity starts at 1 at 0 time, then it decays. There's some noisy. This is at the level of a single realization. There's no averaging here over different Hamiltonians of a disordered system. But then there's kind of a ramp and there's kind of a plateau. If you average over many realizations, you see something much smoother, and you see that all these fluctuations go away. Essentially, you see the first part, again, is governed by the disconnected component. This beautiful ramp, this is what is a manifestation of quantum chaos, and then it's just the plateau. So, by the way, in the literature, sometimes these fast fluctuations in the fidelity are referred as quantum noise, but this has nothing to do with the quantum noise discussed in this conference. Yes? These are just coherent fast fluctuations due to the smaller energy differences in the system, small and large. Good. So we are going to talk about the basic phenomenology of this behavior of the fidelity in a chaotic system. There's a decay towards something, a minimum, we call a dip. Then there's this following ramp, and there's the plateau. By the way, this is of relevant and it has been measured in several systems, not maybe with SYK, but with other chaotic systems. There's a work by, this work by several authors, Vidmar, Prost, and others, that emphasize that what is truly a manifestation of quantum chaos is this ramp between the dip and the plateau. And this is obvious because from the analytical decomposition, this is the part that depends on the eigenvalue correlations. So that's what you take. You say that a system is chaotic if there's level repulsion, if the eigenvalue spacing obeys a given distribution, and so on. So let's choose this, the extent of this ramp, the time interval in which it holds, as a manifestation of chaos. And the longer it is, the more chaotic is going to be the system. This is all in isolation. So now I want to move to open systems. And there are different proposals in the literature. In some sense, there is no obvious generalization of what should be the spectral form factor for open and non-Hermitian systems. So I'm going to pick a given approach. This is what we have been pursuing, is to say that the natural generalization to open systems of the spectral form factor just remains by keeping this interpretation of the fidelity. So it's what we call the fidelity-based approach. And for one thing, it's grounded on quantum dynamics. And because it's an overlap between different states, it's also related to geometry of quantum states, so quantum information geometry. So, this is a series of works since my first work on quantum chaos with Julian Sonner and Molina Villaplana. We have been working on this. So let me tell you a bit about it. So first, just the fact, and actually this was done at ICTS by Subrat Rayu with Papadodimas, was the observation that you can get a complex analytically continued complex partition functions if you start with either a coherent Gibbs state or a thermofield double. That's what they were considering in the context of black hole physics. If you evolve it unitarily and then you look at the survival probability, then you just get this object, which is the one that has been used to diagnose quantum chaos. That's for a system in isolation. Now, if you do the same with an open system, well, you have some initial state, you evolve it with some quantum channel, and then you look at the survival, at the fidelity, which is the survival probability of the time-dependent state in the initial coherent Gibbs state. You can do it for many models, so I'm going to choose a very simple model, which is energy dephasing. Energy dephasing can be shown to just give rise to the time averaging with some filter function here, some Gaussian function of the spectral form factor of the system in isolation. So I'm choosing a simple model of open quantum dynamics where it's essentially just equivalent to time averaging. So I have a system in isolation, I time average its dynamics, and this is the effect of energy dephasing. And here you see an identity for the spectral form factor of the fidelity in the case of open systems. This is what happens then in the dynamics. So you see here I'm reporting for the fidelity of the spectral form factors as a function of time for different values of the dephasing strength. If I have the value with unitary dynamics, then this is the plots, the curves you saw before. You have decay, you have the ramp, and the plateau. This is for one single realization. This is for an ensemble average. Now, what is interesting is that as I increase the strength of the noise, two things happen. First, even for a single realization, all these fluctuations go away. So all this, I wouldn't like to call it quantum noise, but all this quantum noise is suppressed. The other thing you see is that the ramp is shortened because its onset is delayed. It's not, nothing happens to the plateau. The plateau value is the same for all values of the dephasing strength, but the higher the dephasing strength, the more I shorten the value of the ramp. So the dynamical manifestation of Hamiltonian quantum chaos is being suppressed as a result of the phasing. And this, you see it even more clearly when you average over trajectories. Of course, this is the result, we can understand this as a result of 3 different characteristic times. One is the time at which the dip and the plateau arise in the isolated system, and the other is in the case for open systems, the decoherence time. Yeah, so let me use it. So, okay, this is what happens when I'm looking at the phasing. So the phasing reduces the dynamical manifestation of chaos. Now I'm going to show you that if I suppress quantum jumps, actually I have the opposite effect. I can prolong the manifestation of chaos. So for this audience, we can divide the Hamiltonian between the master equation between the effective non-Hermitian Hamiltonian and the quantum jumps. And if in the same model I suppress the quantum jump term, what you see is that for certain values of the dephasing strength, I actually managed to prolong the ramp. So here, energy dephasing in the absence of quantum jumps, so null measurement conditioning enhances the manifestation of chaos, and you can see that the ratio of the plateau time and the dip time actually increases for broad values of the initial state and for many values of gamma, the dephasing strength up to some points. Yeah? So this is spectral filtering allows you to enhance chaos. I think I should close, yes? So we have beautiful analysis in terms of spectral filters giving rise to very esoteric dephasing models and Hamiltonian deformations, but I close here. Have 2 parts, the first one on symmetry breaking, the second one on chaos. So I thank you all for your attention.
Thanks a lot. Are there questions about Adolfo's talk? Is there? Okay, there's a microphone.
I have one question. Okay, sorry. Yeah, this is regarding the slide where Zurich's work was shown. And in the high temperature limit, you get that behavior for the decoherence time. So,
yes, I follow you. Yeah, that's a standard dephasing at high temperature. Yes,
that's right. So, however, if you go to very ultra cold temperatures, close to 0 temperatures, the decoherence follows a power law. The same analysis would lead to a power law behavior.
Power law in what?
Power law in time.
Oh, yeah, well, sure. I mean, we reported the behavior of the purity at all times, but what I say is still true. At short times, you have this behavior consistent with the exponential decay, with this decoherence time. And even if the quantum Brownian motion is not Lindbladian, it's not Markovian, you can still do the formal analysis for this equation, and our results are correct. So this extra term has no effects in the short-time dynamics.
But at long times, I think it would matter, right?
Sure, but here I have a short-time expansion. My analysis is strictly short times. I'm not saying anything about long times. Long times actually, we also report it in the paper, but I didn't comment it here. Yeah, thanks.
Okay, thanks.
My question is regarding the spectral form factor for open quantum systems. So when you define the thermal density matrix, what are the eigenvalues and eigenvectors? Are they taken from the Lindbladian or from the Hamiltonian?
No. So here, this is the difference with, thanks for the question. So this allows me to clarify a bit different approaches. Yeah? So many people are defining dissipative quantum chaos in terms of the spectral statistics of the Liouvillean and the Lindbladian. Our approach here is different. I have a system that in isolation is chaotic. And now I want to see how noise or the coherence in the dynamics suppresses the dynamical manifestations of Hamiltonian quantum chaos. So I want to see how the chaotic systems or the systems in isolation are suppressed or enhanced due to the coupling to the path. You see, so this is different from what people like Prosen, Sa, Garcia, and others are doing, yeah? Or even Manas here in the audience as well.
Okay, thanks.
Hello, thank you. I just wanted to ask you, in this quantum chaos in open quantum systems, people also try the OTOC approach, right? How does, do you have any thoughts on how it compares with your fidelity-based approach?
Yeah, I mean, many, see, there was a huge outburst of interest in OTOC OTOCs because, there's the beautiful result by Maldasenas and Stanford and bounds on chaos and so on. But many systems do not exhibit a nice behavior of OTOC to be able to extract a Lyapunov of exponents. So I think here we are taking a different route so that you can apply to different, pretty much any systems. And, if you want to see explicitly the connection with OTOC in dissipative systems, I refer you to the talk by Aritra Kundu and also the mention in the talk by Aurelia Chenou, where we discussed in a joint collaboration how dissipative OTOCs arise in open systems and govern the dispersion of a given observable in the presence of stochastic of classical noise.
Thank you.
Okay, then Manas.
Yeah. So I had this question about if you remove quantum jumps, you were able to prolong the ramp, right? But we had a situation where removing quantum jumps actually promoted localization. So I'm just trying to which basically means that which will probably kill the ramp. So is it some system dependent thing or is it there's something?
Yes, I got, you see, yeah, excellent questions. Thank you. This is the part that I had at the end. I was going very fast. What we are doing is focusing on spectral filtering. So we want to see how selecting different energy windows or different eigenvalue range of the spectrum alters the manifestations of quantum chaos. That means that I'm naturally working on the language of dephasing or monitoring or in the Hamiltonian eigenbasis. This is therefore very dependent on this, yes? So I don't claim this holds generally if you have dephasing in a different observable. Indeed, we have done it. If you have dephasing on an observable that does not commute with your Hamiltonian, then you don't have a dip or nor a ramp. You directly go from unit fidelity to a plateau in a monotonic decay. So you completely kill any dynamical manifestation of quantum chaos when the dephasing operator does not commute with the system Hamiltonian. So that's even with quantum jumps. So you see, let me give you a different answer. I mentioned these 3 different contributions. What we are doing when we suppress quantum jumps, we are effectively giving rise to a Hamiltonian deformation. The dynamics is governed by a non-Hermitian Hamiltonian. The non-Hermitian part, what it's doing is to kill this part. So therefore, the ramp can have its onset earlier on. But this is very specific, again, to the fact that we are acting on the energy eigenbasis directly through the null measurement condition on the energy dephasing, yes? So we are doing really energy spectrum filtering, and everything I have said has a focus on the energy eigenbasis.
Okay. Thanks.
Yeah. So we kill this term, essentially, and then we only have these 2.
Okay, thanks. We take one last question. You have a microphone.
Hi. For the spectral form factor, this deep ramp plateau is kind of, so it's the expectation out of random matrices, right? So for the open system, what is the expectation? Do you have some expectation out of some random something?
Yeah, so again, there are different approaches, and what I am doing here is to see how the Hamiltonian chaotic features are altered by the coupling to the environment. So from that point of view, I think of the environment as perturbing what I already know about the system in isolation. So here my reference is still that of random matrix theory, Wigner-Dyson distribution, all disordered systems doesn't have to be a random matrix. You take a spin chain, you put disorder, you also have, you know this one. So yeah, that's the case. And again, I emphasize this is a different approach to that one in which I look at I try to, by mathematical generalization, I just say, well, looking at the energy spectrum statistics has worked for isolated systems. So for open systems, I should look at the Liouvillean spectrum. And and again, some people have done it. It's also useful, but we are addressing different aspects of chaos in open systems.
Okay, great. I think we can postpone further questions to lunch, and it's very nice talk.
Thank you all for your attention.